which is going to talk about papers that appeared in machine learning conferences. So it's really quite amazing to see zero-knowledge proofs being used by non-cryptographers for non-cryptographic purposes or non-blockchain purposes, and the results are even published in non-cryptographic conferences. And so, Chhavi, looking forward to your talk. This one.
Hi everyone, I'm excited to be here. So I'll be talking about accountable AI with ZKPs. So as at least we in the AI community think that AI has the potential to be very useful, but it also has the potential to cause great harm. Every day we see some news headline about some crash or like some racist decision that the AI made or some private information that AI models leaked. But luckily, there are some regulatory guardrails in place. So for example, there's EU's GDPR, which demands certain desirable properties from these models. And Biden's executive order, no more, unfortunately. But and the trustworthy AI literature has sort of tried to give solutions to meet these regulatory requirements. For example, for explainability or transparency, we have multiple explanation algorithms. For privacy, we have multiple definitions and algorithms, and same for fairness, etc. But the problem is that a lot of these tools break down due to confidentiality. And the AI ecosystem is increasingly becoming closed off. So models are closed due to IP and legal reasons, and a lot of these trustworthy AI tools, they need access to the model to run. And this leaves the users unable to verify anything because they don't have access to the models. And we will show here that how ZKPs can come to rescue, making AI more accountable and verifiable. So this is the work that I just presented a couple of days ago at ICML. And it's with my collaborators, Evan and Dan at Stanford, and my advisor, Kamalika at UCSD and Meta. So AI models, we know that are black boxes. So in case, like every time it makes a prediction, we don't really understand or know why that prediction was made. And explanation algorithms sort of try to open the black box. For example, if this is a model used by a bank to grant loans and it says that the loan is rejected, then explanation can be something like, oh, because your salary is low, that's why it was rejected. And the traditional use case of explanation has usually been debugging, which is done by model developers themselves who have access to models. So in this paper, for example, it was shown that this chest X-ray classifier was using spurious correlations such as some writings on the X-rays or some pacemaker, etc., to make decisions. So these kind of things can be prevented if we see such spurious explanations. But another use case that is becoming increasingly common is to use explanations to justify predictions to customers. For example, GDPR has a right to explanation for which these explanations can come handy. And these explanations can also come handy to show that the model that a bank is using, for example, is indeed fair. And it can also be used to suggest changes to a person's features so that they can get the loan. So essentially, these explanations work as trust-enhancing tool. But I will say that despite the demand, explanations fail to work as a trust-enhancing tool. And the problem here is just confidentiality and misaligned incentives for which confidentiality actually helps. So if, for example, a bank rejects my loan, they want to tell me, if they cannot tell me that your loan was rejected because your gender is female, because then it's like discriminatory and I can go to court. So instead, banks are incentivized to give me an incontestable explanation. They are incentivized to tell me that, oh, you should get a high-paying job, your salary is low. And this happens because model is confidential, so users can't run anything. Models can be swapped, post-auditing, etc. The models can be swapped for specific inputs. Different models can be used for generating predictions and explanations, and a lot of different threat models have been studied in the explanation literature. And other reasons are that the explanation calculation is also hidden, and there is a lot of non-determinism in explanation algorithms. So because of these reasons, there's a famous paper which says that explanations should not be used in adversarial contexts. And by adversarial, I mean where there are misaligned incentives. So a plausible solution to this problem is just consistency checks. So a customer wants to know that the explanation given to them is correct. So the customer can try to collect multiple input prediction explanation pairs and check whether the prediction and explanations are similar for similar inputs. But this is bad because it puts the entire onus on the customer. And we can imagine how will they collect so many input prediction explanation pairs. And additionally, there's a result which says that auditing local explanations with consistency checks is hard. So what next? Do we give up, or is there hope? So I will say that ZKPs can help us operationalize explanations in adversarial contexts.
Sorry, maybe I missed it. And you said, what's an explanation?
So an explanation, I will show an algorithm later on, but it's it tells you why that prediction was made. For example, it can tell you which features in the input were important to make that prediction.
Okay.
Yeah.
And all this literature says that usually they lie in explanations.
Sorry, usually the literature.
All this literature that you quoted says that you shouldn't trust explanations.
Yes, because of confidentiality.
Okay.
Yeah, because users, you need explanation algorithms run on the model, but users don't have access to the model. Yes?
What are the guarantees of the explanations? So if we run on the same input, we will get the same explanation?
Yeah, so sadly it's quite broken. But there are some guarantees, but we don't actually have very good guarantees about these explanations, but sometimes they work and give us good insights. Yeah, people are trying, but the state of the art is not very good. And this is a very active area of research, making explanations faithful, sufficient, etc. So in our protocol, on the one hand we have a bank, and on the other hand we have a customer. So customer asks a query, for example, applies for loan, and then it gets an inference, a prediction, and an explanation. But with zero knowledge proofs and commitments, this is how we modify it. So initially, the model developer does a commitment to the model, and this is only done once. And after that, for every query that comes in, the bank gives an inference and a proof of inference, and it also gives an explanation and a proof of explanation, which is then verified by the customer. Yeah.
If you have query access to the model.
If you have what? Query access to the model.
Yeah. In the previous scenario where you had that example that a 20-year-old female with 3K salary is denied a loan. If you could send a spurious query like 3K instead of 3K, let's say 10K salary, if the model still answers the same, then you would have an inference already.
Right. So what we are assuming here is that it may not be so easy to do these API queries with models. It's easy for chatbots, but then if you have a bank, you need additional documentation, it's not easy enough.
So the assumption is that the inference algorithm is public?
The inference algorithm, yeah.
It's public. I see just the data is, but there is an inference algorithm which everybody agrees this is the right way to do it.
The inference algorithm is public, the model is confidential.
I see.
Yes?
Big question. Do we understand about enough about AI and those inference models that the meaningful explanation could be just said, oh, it's because of the gender or salary? Because I saw it's this crazy model, nobody understands what is going on.
Right.
So do we understand enough? Is it something feasible?
As I said, this is a very, very active area of research. So we are getting somewhere, I hope. And this is a bit forward-looking, I would say. But still, I think the explanation algorithm that I will show you, you will see that the citations are pretty high. So probably it's used a lot. And there are libraries developed by people, also by companies, to implement these.
So the way to view this at this point is if we're happy with an inference algorithm, an explanation algorithm, given access to the model, then this is a way to do it without seeing the model itself.
Exactly.
But the hypothesis may not be true today, it may be true in the future.
Yes. So these are some of the guarantees that we would require. Firstly, that the same model and the same explanation algorithm parameters are used for all inputs. So it's not giving like a constant function reject for black people and the actual model for white people or something like that. And then the explanation and prediction should be generated using the same model. The generated explanation and inference, they're correctly computed without manipulation, and the model confidentiality is still maintained. Yeah, and here in this paper, I will not talk too much about inference proofs because we use Ezekiel as a plug-and-play library, but this is the state of the art for proofs of inference. So a VGG model, which is an image model, and it has 15 million parameters. It takes 2.2 seconds to generate a proof of inference per image. And for Llama 3 is like the premier open model in AI right now, and it's 8 million parameters. It takes 150 seconds per token per word.
I have a question. Usually people take for granted that proof systems are publicly verifiable, but in this use case, isn't it enough to use a designated verifier proof system? Like the original notion of zero knowledge? It could be faster.
Maybe Dan can answer that.
It depends, right? It depends on the application. Maybe you want to be able to show the explanation to somebody else. Say the model treated me unfairly, so...
I'm not saying it's useless. The question is whether you have settings where designated verifier proof systems suffice. So then maybe, you could do better.
Yeah, could work, yeah.
But that's 8 billion.
Oh, sorry.
8 billion.
Yes, mistake. Okay, so I can move ahead.
Actually, if I could just add, so 150 seconds per token is kind of surprising that it works so fast. That you can do proofs in such large models so quickly. But then at the same time, 150 seconds per token is not quite usable. Yeah?
Right.
You can't wait 150 seconds for every token.
Yes.
So there's more work to do, but it's interesting how far the field has already come.
Yeah, I think it's very, very surprising.
How should I think of a token? Is it like a syllable or a
so token, roughly you can think of it as a word, but tokens are like, a word can be broken down into multiple tokens.
So what is a token?
A token is like a word broken down into multiple, that could be a token. I mean, a single word broken down into multiple parts could be a token, but roughly you can think of it as a word. Yeah, the point here is that we are surprised that we are able to do this, but then there's a lot more to be done.
Thanks.
Yep, so we are using Ezekiel pre-existing module to do proof of inference, so I'll not talk much about this. Yeah, and now the question that everybody wanted to know about. So this is a very popular explanation algorithm. It's called LIME. It stands for Local Interpretable Model Agnostic Explanations. And there are multiple libraries developed by both industry and individuals to run this explanation algorithm. So the way it works is it wants to approximate a local decision boundary around an input with a linear one. So our original machine learning model can have a complex decision boundary. Here, like the curves are the decision boundary. And like the input is the thing in red, and we want to approximate it, approximate the decision boundary around that input with a linear classifier. And this is like the coefficients of the linear classifier work as explanations. So if this is the linear classifier that we come up with, then your salary has a weightage of 0.8, education of 0.4, and age of negative 0.5. Yeah, and this is the algorithm. So the input is the complex model and the input point. And the way it works is it samples n points around the input, and then it weighs them according to the distance from x from the input. So you see some points are larger and the others are smaller. And then it gets predictions for sample points according to the original model. And then it fits a linear model on top of these sample points. So step 3 gives you the labels. Step 1 gives you the the inputs. And then you train a linear classifier on that. And then you return the linear model coefficients as explanations. Yeah?
So it seems here that this algorithm does not require knowing how the model F works, but only knowing, like, only having access, like Oracle access to it, like sample the endpoints and just ask the model about them.
Yes, but we need to know that the inference is correct.
Where do we check that?
So this is the original line without ZKP, but I will, like in step 3, you would want to check it, right?
Oh, so this is like, you say that the problem with this is that I don't trust it, not that it reveals too much.
I don't trust that the labels are coming from F or not. That's what I don't trust. Yeah, because you can imagine if the labels are different, then the linear classifier which is trained on the labels will be different, right? So the explanation will be different.
How privacy, I mean, is it preserving or non-preserving this? I mean, deploying this thing, if you release this classifier, probably, I would guess it leaks something about the input.
Yeah, it leaks something about the input, but you might need a lot of samples to actually reconstruct the decision boundary, which increases with your dimension, I guess. And also, not everybody is adversarial, right? Like, so even for non-adversarial users, we still want them to be able to verify. Okay, now there are some technical challenges if we want to implement this LIME in a ZKP library. The first one is that if you want to train a linear classifier, you need access to an optimization solver. So a strategy can be to verify instead of re-implementing. So we can use some duality gap checks, or if our optimization solver has a closed form check, then we can try to check that. So instead of re-implementing the optimization algorithm, this is what we try to do. And another challenge here is that ZKPs introduce additional computational overhead. So one way to do that is to just engineer ZKP libraries or whatever your ZKP code is to make it faster. But another way can be to shift ML models towards being more ZKP amenable, ML algorithms to be more ZKP amenable. So this is the approach that we will try to take. Yeah, and I will give some short explanation of how we try to do that, how we try to make LIME more ZKP amenable. So as you can see, the first 3 steps are repeated n times. So you sample a point, then you weigh them according to distance to the input, and then you get predictions for the sample point. So you do this n times. And maybe we can modify some stuff here to make it better. So instead of, we can play around with different sampling techniques, and we can play around with different weightage or kernels, for example, exponential or no kernels. And for sampling, we check like Gaussian and uniform, and this results in 4 variants. And yeah, so what we want to check here is that even like we modified ZKP, we modified LIME and came up with 4 variants, but the different variants should give equally performant explanations because we don't want that quality to degrade. And the other question that we want to see is any one of them better in terms of ZKP cost? So we will experiment with tabular datasets. So these are 3 very famous credit datasets in the AI literature. And the models that we will use are small neural networks and random forests. So this is the state of the art. These small neural networks and random forests are enough to get state of the art accuracy on these tabular datasets. Yeah, now to check this, we want a metric. So we will see performant here, meaning that the complex model predictions should match the linear model predictions, right? Then we know that the linear model is approximating the complex decision boundary accurately in the local region. So this is the ratio that we will care about. Yeah, and we see that So on the x-axis, we have the 3 data sets. On the y-axis, we have our prediction similarity metric. And the 4 bars here stand for each variant. So Gaussian plus exponential kernel, Gaussian plus no kernel, and so on for uniform. So we see that these are like, there's not much difference in the explanation predictions. Yeah, and in terms of ZKP cost, we see that Gaussian plus exponential takes the most amount of proof generation time. And that's just because you have to do exponentials in both Gaussian and exponential kernel. But in uniform plus no kernel, you avoid some checks. Yeah, and here we are at around 1.1 minute for uniform plus no kernel. And verification time is around 0.1 seconds. And the proof size is pretty small. It's 10 kilobytes. Yeah, so we wanted to do an ablation study to see like how does the ZKP overhead increase with increasing hidden layers and units per hidden layer. So we see that it's almost going to go up at least polynomially or exponentially. So on the x-axis, we have the hidden layers, and on the y-axis, we have proof generation time. I'm talking about the first picture here. And we see as we increase the number of units in each layer, our proof generation time increases a lot. And the same for verification time. So yeah, we wanted to know like what increases this rise in time with the model size. So we'll just look at first 2 steps. So we want to like find the time for each of these steps. So the first 2 steps we club into one. The third step is getting inference and proving inference, and the fourth step is checking the linear model. And we see that as we increase the hidden layers, the sampling and the kernel proof generation time is almost the same. It's 24 to 25 seconds. And checking if the linear model is correct or not, that is also around 60 seconds. But we see that the question that you were asking about proving inferences, that increases as the model size increases. But the good thing is that this is, I suppose, a very active area of research, and this time is going down. Yep, so to sum it all, we operationalize explanations in adversarial contexts using cryptographic tools, and this works for confidential models, has a manageable overhead. Yeah, may I know how much time I have left?
Yeah, I think it's actually.
We don't have time? Okay, it's almost done? Okay. Yeah, so this is another similar paper which gives a proof of fairness. So we want to publicly verify fairness of a model. And the canonical approach is external auditing. So a third-party auditor uses API queries to estimate fairness. But then this is shown to be very leaky. And what if the models are swapped post-audits, and if these audits can be sensitive to the choice of reference auditing dataset? So so this is FairProof. So instead of explanation, we have fairness certificate here. And we have some algorithm to give the fairness certification in the clear. So I don't know if people want to know about this. We use this fairness definition that similar people should have similar predictions. And we sort of make some connections with adversarial robustness literature, which is kind of similar, but doesn't have the notion of a sensitive attribute, such as race. And then we use that algorithm to give the fairness certificate in the clear. And we see that our algorithm is able to distinguish fair and unfair models. And then the ZKP time is here. So we divide our ZKP system into online and offline proof generation. So offline proof generation can be done once before deployment, and it's around max 1.5 minutes. And the offline proof, so that was offline proof, and online proof is around 4 minutes, and the verification time is around 3 seconds max. And the proof sizes are pretty small.
Again, what is it you assume? So you're proving that it's fair under the assumption of, there's some assumption
So,
Like before you assumed something about the explanation. Now what are you assuming about?
so we are assuming that there is a fairness algorithm which can tell us how fair the model is, and we want to implement that in ZKP because it's hidden.
To implement,
Maybe I'll add that, so there's a committed model.
yeah,
So you want to prove properties with respect to the committed model.
yeah.
So for example, here, the property is this individual fairness, which says that when you submit a point, all the points around your point are classified the same way. So the model isn't using prohibited attributes to make its decision. So this is proving uniformity. So given a particular point, it's proving all the points around that point are classified the same way.
But this model is randomized, this committed model?
The model is no, the model is not randomized.
But if we think about like a large language model,
This is not LLMs. These is for making mortgage decisions.
these are
oral decisions,
classifications, and they're not randomized.
They're not randomized.
Okay.
Yeah.
Yeah, so in the interest of time, this is all I had, and so these are some of the challenges that I came across while implementing the system. Like I found as a non-ZKP person, I found the coding, documentation, and community support to be very, very low. Yeah, it was very hard to code. This had almost traumatized me. And the other assumption that we are making in all of these is probably that the architecture of the model is public, but that's not okay from an ML perspective. Yeah,
You mean you assume that everybody knows the circuit or something?
Yeah, so ZKPs might be a promising solution for auditing or verification requirements of AI. And we provide 2 examples with fairness and explanation. And some future directions are how do you scale these to bigger models, or what different properties can use this kind of verification from a societal perspective. That's all I have.
Yeah, I don't know. I think what's interesting here is the ML community is kind of picking up the ZK tools, which is, I don't know, everybody just tap their backs for this. It's kind of amazing to see this actually happening.
Yeah, so this time at ICML, there were many papers on ZKPs.
Yeah, so it's kind of
increasing.
You're saying that the world of ZK, or ZK, whatever, is kind of taking over the rest of the
Yes.
universe, including the ML space.
Yes.
Which is great. Yeah. So let's see.
It's important to just conciseness. You actually zero knowledge.
ZK aspect.
Yeah, here ZK is important because
Find a better, it's not
The model.
what's leaked about the model. Yeah. Great. Any other questions? All right, fantastic. Oh, yeah, please.
Then when it ZK.
Sorry, what were the?
What were the contexts that you tested on?
So this is non-LLM.
But in the first, like, these ExpProofs?
The first SOTA time that I showed, right? I forget. I'll have to check in the paper. So this is not our paper. The SOTA thing that I showed.
Okay, then never mind.
Yeah.
Very small.
Also, the
this is
explanation
not
is a
ours.
deterministic thing?
Sorry.
Also, the result on explanations is a deterministic assumption of the model?
So there is randomness involved, but we need to fix it.
Commit to it.
Yes.
You prove a PRG ran correctly.
And your experiments are with that?
Yes.
How much is the randomness? It's like a seed or something?
Yes.
Cool. All right. Thank you, Chhavi.
Thank you.
So we're going to break for lunch, and we'll be back here at 2 for Justin's talk.
Not like a minor scale.